teman-teman setianya Pak Hadi.
Wow, thank you. Saya lihat Pak Devi, you punya engineer ada 9 orang kali yang daftar.
Gak apa-apa kan, biar rame.
Perusahaan nggak tutup dong ya?
Nggak, kita semua kan dari rumah.
Oh, dari rumah. Bagus.
Selamat pagi Pak Hadi, sehat selalu Pak.
Pak Sugeng ya?
Bukan Pak Hadi, saya tadi Pak Hadi kalau nggak salah ya.
Oh Hardi ya,
Hardi.
Itu ya.
Mantan anak buah.
Oh ya Pak Hardi, ya saya lihat. Barusan tadi Pak Sugeng ya suaranya ya?
Iya Pak Hadi, kapan Pak Hadi ke Indo?
Ke Indo nungguin Pak Sugeng. Biar nanti diajak makan.
Ya, sama Pak Devi juga tuh.
Oh iya, bagus.
Halo, ini Pak Sugeng di mana nih? Di New Zealand atau di Jakarta?
Saya masih di New Zealand nih Pak Wira.
Oh, I see. Ya. Ini Wira nih.
Ya Pak Wira.
Lama nggak ketemu kita.
Betul Pak Wira.
Hai Pak Hadi.
Halo, siapa nih, Elmi?
Yes.
Oh, Elmi, hai.
Hi everybody.
Yosi ya?
Hai.
Barusan ada itu juga, ada Steven Widartawan ya? Bang ya? Masuk?
Not sure.
Not sure, ya. I can see the names.
Oke, kita mulai saja bagaimana. Pak Hadi, for the sake of time, Pak Dayu, mungkin kita mulai saja. Saya buka sebentar ya. Saya mute dulu for a moment. Alright, so selamat pagi, selamat siang, selamat sore, selamat malam, Bapak Ibu sekalian. Ya benar, selamatnya banyak sekali karena ternyata saya dapat bocoran partisipannya from all around the world. Okay? Ada yang di Amerika, New Zealand, Australia, Indonesia, Southeast Asia, jadi di mana-mana. Jadi on behalf of Pak Wira Chong, Ketua ICESNA, saya Edwin Lim ingin mengucapkan terima kasih yang sebanyak-banyak dulu terhadap Pak Hadiyap selaku pembicara pada sesi webinar kali ini, dan tidak lupa juga terima kasih kepada Pak Dayu, sekarang adalah PhD candidate di UC Berkeley, sebagai moderator webinar kali ini. Tentu saja terima kasih Bapak Ibu, saudara-saudari sekalian yang sudah meluangkan waktunya di pagi hari ini untuk ikut berpartisipasi di bidang teknik sipil ini bersama ICESNA. Ya, terima kasih banyak. Tidak disangka tahun ini ICESNA berhasil menyelenggarakan 7 webinar secara total. Sejak ICESNA berdiri, kita sudah menyelenggarakan kurang lebih 13 webinar. Jadi check it out, right? Next year, ya, more webinar dari ICESNA. Okay? Sekaligus mungkin ini adalah ICESNA webinar terakhir tahun ini, dan mungkin itu saja sepatah dua kata ya dari ICESNA sendiri. Without further ado, Pak Dayu selaku moderator, the screen is yours.
Oke, terima kasih Edwin. Sekali lagi selamat sore, selamat malam bagi rekan-rekan di Amerika dan di Kanada. Juga selamat pagi bagi rekan-rekan di Indonesia. Selamat datang di webinar ICESNA. Ya, sebagai informasi, saat ini partisipan yang bergabung sudah lebih dari 50 orang, dan pastinya akan bertambah lagi karena yang pendaftar sudah lebih dari 200 orang, dan itu tersebar di seluruh dunia dari Amerika Serikat, Kanada, Indonesia, dan berbagai negara lainnya. Tentunya ini merepresentasikan minat yang besar bagi para civil engineers mengenai topik webinar kali ini. Sebelumnya saya sampaikan dulu, webinar ini agendanya akan disampaikan, total akan berlangsung sekitar 1,5 jam, kemudian kira-kira 1 jam presentasi materi dari Pak Hadi, dan kemudian dilanjutkan dengan sesi tanya jawab. Mudah-mudahan kita bisa punya sekitar 15-20 menit. Kita akan mengakhiri sesi webinar ini dengan foto bersama, jadi pastikan kehadiran rekan-rekan sekalian hingga menit terakhir biar bisa ikut foto dan biar eksis gitu. Selanjutnya, Sebelum memulai seminar, saya bacakan dulu tata tertib umum dari webinar kali ini. Jadi, bahasa yang kita gunakan adalah bahasa Indonesia dan atau bahasa Inggris. Tapi mengingat banyak yang dari Indonesia, mungkin Pak Hadi bisa mayoritas pakai bahasa Indonesia. Untuk pertanyaan nanti silahkan saja senyamannya, mau bahasa Indonesia atau bahasa Inggris. Kemudian saat presentasi, peserta wajib mematikan suara, mute, supaya webinar dapat berlangsung secara kondusif. Akan tetapi silahkan berikan komentar atau pertanyaan kapanpun melalui fitur chat di aplikasi Zoom. Jadi silahkan saja kalau ada yang mau ditanyakan perihal presentasi yang disampaikan, langsung di chat. Atau kalau misalnya ada yang punya case dan mau berbagi atau tanya-tanya, silakan. Mumpung ada Pak Hadi juga di sini. Kemudian pertanyaan-pertanyaan akan kami organize untuk nanti dibacakan pada sesi Q&A. Tentunya bergantung dari waktu. Bisa dibacakan semua atau tidak. Langsung saja saya perkenalkan pemateri kita kali ini, yaitu Dr. Hadi Yap. Beliau adalah profesional engineer dan juga profesional geotechnical engineers di Amerika Serikat. Terakhir, Pak Hadi practicing di Langen Engineering. Untuk rekan-rekan di Indonesia, sebagai informasi, Langen ini salah satu engineering firm yang sangat reputable di Amerika. Selain di Amerika, Pak Hadi juga pernah berkarir di Singapura dan di Indonesia, baik di industri, di engineering firm, dan juga sebagai akademisi, pernah ngajar di UI, UPH, dan NTU Singapura. Pak Hadi mendapatkan degree S1 di UI, kemudian master di AIT Thailand, dan terakhir S3 di UC Berkeley. Ini di bawah bimbingan Profesor Harry Bolton-Seed dan Profesor Mike Duncan. Buat rekan-rekan geoteknik, pasti sudah kenal dengan dua nama besar ini. Profesor Harry Bolton-Seed adalah founding father Geotechnical Earthquake Engineering. Kemudian Profesor Mike Duncan adalah salah satu pioneer di bidang computational geomechanics yang membawa nonlinear hyperbolic quantitative model untuk pemodelan mekanika tanah. Untuk rekan-rekan yang practicing di bidang desain dan konstruksi bangunan gedung, bisa juga membaca karya Pak Hadi di buku ini, Tall and Super Tall Buildings, Planning and Design tahun 2014, khususnya di chapter Geotechnical and Foundation Design, itu Pak Hadi co-authornya. Ya, sekarang kita masuk ke acara inti seminar. Sebagai pendahuluan, webinar kita kali ini berjudul Design and Performance of Several Shoring Systems in San Francisco. Topik ini sangat relevan untuk proyek konstruksi bangunan gedung dengan multi-level basement atau konstruksi dengan galian dalam lainnya. Pada konstruksi galian dalam, kita perlu sistem struktur penahan tanah atau shoring systems yang reliable dalam menjaga stabilitas geoteknik dan juga meminimalisasi deformasi tanah. Apa saja jenis-jenis sistem struktur penahan tanah ini? Di webinar kali ini akan dibahas beberapa, yaitu antara lain soil nailing, soil cement mixed wall, soldier piles, dan diaphragm wall. Selain sistem strukturnya, juga akan dibahas structural supportnya, yaitu antara lain tieback system dan internal bracing. Supaya lebih aplikatif, desain dan performance dari sistem-sistem tersebut akan dibahas melalui 4 project case, antara lain the Center Building, Bridgeview Condominium, Four Seasons Hotel, dan Oceanwide Center. Semuanya di San Francisco. Saya pikir untuk Pak Hadi, silakan Bapak bisa share screen Bapak dan mulai presentasi. Saya serahkan ke Pak Hadi.
Pak Hadi bisa unmute dulu.
Oke, bagaimana? Baik, bisa didengar?
Sudah jelas suaranya dan layarnya juga sudah kita bisa lihat.
Oke, mari kita mulai. Selamat pagi, selamat siang, selamat sore, selamat malam, teman-teman di mana-mana saja kalian berada. Hari ini saya beruntung banyak teman-teman join dari terutama dari Indonesia, mungkin 90% dari Indonesia. Juga ada beberapa orang dari New Zealand dan Australia. Seperti dibicarakan oleh Pak Dayu, topik hari ini adalah mengenai dinding penahan tanah atau temporary shoring system untuk konstruksi basement excavation. Mudah-mudahan ini adalah yang kalian expect untuk didiskusikan pada webinar ini. Okay, during the past 2 decades or so, we see the skyline of San Francisco has been changing. This is the skyline that we saw in 2007. Fast forward to 2021, you can see there are so many more high-rise buildings in San Francisco. Most of these buildings are on the south side of the Market Street, which divide the San Francisco downtown into two. The companies that I've been affiliated, namely Travel and Rollo and lately Langan Engineering, were blessed with the trust of our developer clients. They have been the geotechnical engineers for most of these buildings. So because of that, I've been practically involved in practically all of these deep excavation projects in San Francisco. So in this webinar, we will talk about 4 different systems. One is soldier piles and lagging. The second one is soil nailing. The third one is soil cement mixed walls or deep soil mixing, DSM. And the last one is concrete diaphragm walls. The general design consideration that govern the design of the shoring system include looking at the base stability for clay, bottom heave for sand, looking at the structural consideration, failure conditions, and construction-induced ground motion. So let's first look at the base stability for clays. This was has been looked at by Tersaghi as early as 1943, and Bierum in 1956. Because of the excavation of the basement for basement construction, you can see that there is a loss of equilibrium in terms of confining pressure. So there is a tendency for these columns of soil to rotate and come out toward the base of the excavation. This is called base heave or base instability. So Tersaghi looked at this problem as early as 1943. And the way he looked at this was that he assumed that AB is in an imaginary footing. So there's these soil columns that load this imaginary footing that wants to make it fail toward the excavation. So that's how he looked at it. Bierum on the other side looked at this as a negatively loaded footing. So they look at based on 2 different scenarios, and because of that, the factor of safety that you get from this evaluation are not the same. Basically, you get a higher factor of safety when you use the Tersaghi method. When we have sand and there is groundwater table, and you make an excavation here, you will see that there will be a seepage coming toward the ground, coming toward the excavation. So you can draw a seepage diagram that looks like this. And because of the difference in water table or difference in water pressure head, there is a tendency for this column of soil here, immediately adjacent to the excavation, to kind of want to move upward. So that happens when the confining stress, effective confining stress within this soil column becomes zero. So this column of salt becomes unstable, and that is a phenomenon that we sometimes call boiling or piping. So boiling and piping is practically a kind of like static liquefaction, because liquefaction is also a case where you have your effective stress in the soil is equal to zero. Now look at the other situation where you have a clay layer like this. When you have a clay layer like this, seepage cannot occur readily because of the impervious nature of the clay. But here you have, so therefore the beneath this clay layer within the excavation, you have this upward pressure that wants to uplift this layer of clay. So for that situation, we will need to reduce the pressure with this descent layer so that it will not cause upheave or bottom heave condition in sand layer. We also need to look at the structural components of the shoring wall. So, for example, you may have a failure if your tendon is weak. So if the tendon broke, you have a failure condition here. This case here is where your skin friction between the grout and the soil is not adequate to resist the tieback pressure. So there'll be your wall can also move outward. This is a situation where where the skin friction between your tendon and the grout is exceeded by the outward force on the shoring wall. So you also have kind of slippage condition here. This situation is where your shoring wall is not strong enough. So you have a extensive bending condition. This situation is where your embedment into the ground is not deep enough. So you have a kind of like a passive failure here. This is the initial stage of your excavation where when you have not installed your tiebacks. So you may cause it to fail by rotation. This is the situation where your embedment is not deep enough. Remember that this tieback is normally installed at an angle of 15 to 20 degrees. So there is a vertical component of the tieback force that needs to be resisted by this embedment, the skin friction of the embedded portion and the soil around it. So to remedy this situation, you need to deepen the embedment depth. This is the situation where your tieback, the bond section of the tieback is not far enough. You might have this kind of overturning, like a block failure, but overturning kind of a thing. This case is similar to this and also similar to this. This is called a rotational failure, mass stability problem. Clough and Urok in 1990 described the shape of the deformation of the shoring wall. So this this diagram shows that the shape of the deflection of the shoring wall takes this kind of shape, and the ground outside the excavation may settle in this manner. And he explained that the shape of the deflected shape is a combination of two factors. One is cantilever movement that occurs before you install your tiebacks. So this is the kind of deformation that you have outside your excavation. And as your excavation goes deeper, you have additional movement that is shown by these dashed lines here. And this dashed line is accompanied by the ground settlement outside the excavation in this manner. So when you combine this and that, you have this kind of a deformation characteristic shape. And when you combine this movement and this movement, you have this kind of deflected shape. Most of in general, the maximum deformation or settlement of ground occurs within a short distance from the shoring wall. So let's call this delta V max. Call this delta V max. And the maximum lateral deflection normally occurs around the level of the excavation. So this is typically larger than the deflection at the top of the wall. So let's remember that, as we can show the later in our case histories. Now, Clough and O'Rourke in one of the proceedings of a conference on performance of shoring walls, they submitted a paper that they gathered the data from 4 or 5 different types of shoring. You can see here saw cement walls, drill pier walls, saw nail walls, diaphragm walls, and soldier pile and lagging shoring system. So they combine all this, and except for a few outliers in here, 1, 2, 3, 4, 5, most of the lateral wall movement, maximum lateral wall movement, that which I call delta H max, as a relation to the depth of excavation, falls within this zone. The maximum lateral deflection is about 0.5% of the depth of the excavation. Remember that, 0.5%. So if your design is decent and the construction is decent, you can expect that you might have a 0.5% of the maximum deflection on the shoring wall. What does it mean? It means that if you have a 20-meter excavation, 20 meter, you might have maximum lateral deflection of 10 centimeter. 10 centimeter, that's about 4 inches. The average performance of the shoring walls is indicated by this line here. So the mean maximum lateral deflection of the shoring wall, according to this study, is about 0.2% of the maximum depth of excavation. So for example, if we have an excavation that is 20 meters deep, 20 meter juga, if your shoring wall is designed and constructed like the actual of practice, you can expect you have 0.2% or about 4 centimeters, 4 centimeter That's about 1.5 inches of deformation. If you do an average job in your design and construction. My question to you is, can you do better than this? Can you do better than this? It'd be nice if you can reduce this to 0.1%. What does 1.1% mean? 0.1% means that if you have a 20 meters excavation, your maximum lateral deflection of the shoring wall is about 2 centimeters. 2 centimeters is about 0.8 inches. So it's less than 1 inch. And that's what we all hope for. That is, if you can make you can design and construct a shoring wall that only deflect, maximum deflection is only 0.1%. That is about 2 centimeters. You're doing hell of a good job, very good job. You can do that by, for example, designing for a little bit higher pressure. We'll discuss that a little bit. And also maybe deepen the embedment. These are the third method is maybe to improve the ground if you have a soft soil below the excavation level. Why is this important? Well, why is it important to maintain a small deflection of the shoring wall? It's because the settlement of the ground surface outside the excavation is roughly equal to the maximum deflection of the shoring wall. So this deflection is roughly equal to this. Well, according to the statistic, this is about 75% of this. So here you can see that the average ground settlement outside the excavation is about 0.15% of the excavation height. So if you have a 20 meters excavation, your ground settlement outside, you can expect, if you do a good job in designing and constructing the wall, you may have a settlement of around 3 centimeters. 3 centimeters is about what? Maybe like 1.25 inch, something like that. So the reason this is important is that you might have adjacent building that is maybe kind of old, maybe brick, maybe unreinforced outside your excavation, and that they are sensitive to differential settlement. So you want to make sure, you want to try to maintain the ground settlement outside your excavation as small as possible to reduce the potential for damage to that old building. This is a chart that was put up by Clough in 1989. This is the maximum lateral wall movement versus excavation depth in percent. And this is for the case where you have soft to medium clay. Soft to medium clay. They suggested that the effect of that the deflected shape of this wall is a function of your base factor of safety against basal heave. We have talked about this a little bit about basal heave in clay. So if you have your factor of safety against basal heave is as high as 2 or 3, your maximum deflection of the wall maybe are less than 0.5% of the wall height. But if your factor of safety is only 1 to 1.1, you may have 1% of deflection. That's pretty high. And so therefore, it's important to check the factor of safety against basal heave in all excavation project. Now, let's look at other factors that may need to be considered in design of shoring system in San Francisco Bay Area. Actually, this is not just San Francisco. I think everywhere where you are, Indonesia or elsewhere, the same problems may also apply to deep excavation because some of these problems are common to all. For example, you have adjacent old buildings, some with basements. So there's something that you need to consider in your design of your shoring system. And you may have a random fill on your site. What's the problem with random fill? The problem is that they may not give you an adequate skin friction for your tiebacks, for example. High groundwater level, there's an issue that you have to deal with because you don't want to have a problem that you have a piping or boiling or basal heave in your excavation, as we have talked about earlier. You may have a soft clay problem. Soft clay causes base instability. Dune sand is a wind-blown deposit that is present in San Francisco. Dune sand is typically loose to medium dense, so the skin friction of the tiebacks would be lower than if it were a dense sand, for example. You may have underground utility lines. Now, this may affect where you can install your tiebacks because you don't want your tiebacks to puncture these underground utility lines. We have a situation where you may have this high voltage line, maybe, or you may have these telephone lines that you don't want to disturb. Because if you puncture these phone lines, you may close down the communication in the city, and we have some of that problems before. You may have utility walls under your sidewalk. Sometimes you have under your sidewalks you may have electrical vaults or something else that you have to be mindful of. And in another case, you may have subway structures. We have BART in San Francisco Bay Area Rapid Transit System that is similar to MTR or MRT in Indonesia, Singapore, and Hong Kong. So we have to make sure that our shoring design does not impact this subway structure. Let me show you a map here. Now, this is Market Street in San Francisco. There is a subway structure here underneath this Market Street. One is for Muni. This is the cross section. You take a cross section of here, AA. These two tunnels they belong to Muni. Muni is a municipal train system, electric train system, that in the rest of the city, they come on the street level. But within this Market Street, they go down below the street level. Then they are on top of these BART tunnels. BART is the Bay Area Rapid Transit System. That is similar to MTR and MRT that connects connected the cities like San Francisco, East Bay in the Oakland, and Pittsburgh, and Concord, Walnut Creek, and South Bay, including the South San Francisco and Mimbarnya station. So once in a while, you have this connecting tube between these two tunnels. And between at the few 100 yards or so, you have this terminals station, subway station, where people could go down and go on board of these BART lines, BART tunnels, or muni tunnels. So, but sometimes these tunnels not only go under the street, they may go under your site. I have some one or two slides to show you later on. But if you take cross section here in your typical site, for example, in San Francisco, you may have a situation that is depicted in this diagram. So this is a site where you have a tunnel, and this is your building. This is located on Market Street. If you take a cross section like this is your muni line, this is your BART line, and this is your building. All right, this is your building. So if you want to develop this site, if you want to demolish this building and develop into a multi-story high-rise structure, you may excavate deeper. You may install new shoring walls, and all of those construction are governed by a set of guidelines that is established by BART authorities. We are fortunate that we have a lot of experience in this kind of a situation. We've probably done between 10 and 20 of this development where we are adjacent to muni and BART lines. And one of our case histories that I'm going to show later today is going to show you that situation. This is one of my project site in San Francisco. This is called, this is Market Street that I showed you before. And this is South Venice. The site is called 10 South Venice. This is a triangular site. And this, the muni, as I showed earlier, there are two muni tubes on top of BART tubes. The muni tubes go upward and appear at the street level on Market Street. But the BART tubes remain at the same elevation, go underneath my site. So if I take a cross section AA prime, I can show you here. This is the situation. This is the two BART tunnels or tubes that goes under my site, and this is from here to here. We're gonna have a podium. From here to here, we're gonna have a tower, and here to here is gonna have a mid-rise. So you have this situation. You're gonna build on top of BART tunnel. There is a lot of guidelines, and your design will be reviewed by BART. What is the what are the guidelines? The guidelines is that I'll start with number 2. The soil distribution caused by the temporary shoring or permanent foundation system shall be analyzed because they don't want these structures to be subjected to pressures that exceeds the design pressures. Number 3, shoring shall be required to maintain soil at rest condition. So in soil mechanics, we have active, at rest, and passive. So they're gonna want you to design your shoring under at rest condition that is slightly higher than your active pressure. And if you're within the number 4, if you're within the influence zone, you have to pre-drill. If you're going to use driven piles, you have to pre-drill below the influence zone. I will show you what influence zone is later on. Number 5, if you are going to do a piling operation, you have to monitor the vibration close to the subway. The tunnels have to be also monitored for vibration of movement. The water level cannot be lowered. They have to be monitored and make sure they are not lowered more than 2 feet below the pre-existing water level. And you cannot build your structure closer than 7'6" to their butt structure. 7'6" is what, about 2.3 meters maybe. I'm gonna skip this and I'm gonna show the next slide. I'm gonna skip this. We have a lot to cover. So this is the influence zone. This is the bar tunnel, this influence zone. So what they're saying is that if you use drill piles, driven piles, you have to pre-drill below this influence line such that your vibration, there's no loading that is induced on this bar tunnel. You have to pre-drill to 10 feet below this influence line before you can go on driving your piles. But driven piles is seldom used in San Francisco right now because of the noise issue. So people normally revert to drill piles, drill piers, or board piles. So if you use board piles, you have to use double casing in this depth, in this zone. Double casing to eliminate any friction within the zone of influence. Because if you have a friction, skin friction here, your load can be induced to this part tunnel, and they don't want that to happen. So you have to have a double casing in this situation. So what happened here? How come? Let me see here. Okay, I somehow lost it. I don't know why, but anyway, what happened here is that within this right of way, the loading cannot exceed previous loads. So when you have a podium, the load imposed by the podium cannot be higher than the pre-existing pressure within this zone. Here, when you have a tower, this tower will be like 42-story building. Within this zone, we have to use double casing piers because they don't want to have any loads to be induced to these tunnels. So, so that will be their requirement. All right, it works. Okay. I have 4 case histories that I'm going to show. So we have about 30 minutes to go. So I try to make this 7 to 8 minutes for each case history. So number 1 is what is called a Bridgeview Condominium. We have a developer that wants to build a condominium on the north side of this Bay Bridge Anchorage. Yeah, this is Bay Bridge Anchorage. Bay Bridge connects San Francisco and Oakland in the East Bay. and it is traveled by about 260,000 vehicles a day. So the Caltrans that is in charge of this, they are very thorough in the review of our design, because any problem, any deformation problem with the Bay Bridge anchorage, that's going to be a nightmare, because this bridge is well traveled. Can you imagine 260,000 vehicles a day? So this is the project site, and located on Bill Street. So this is Bill Street. This is looking north. So this is the Bay Bridge anchorage looking from the south side. The project is located on the north side. Here. Now this building is about 16 to 18 story tall, but it's only 20 feet away from this Bay Bridge. So you can imagine that you know, it's people are feel very concerned, and you can see that the name of this condominium is Bridgeview, because this condominium is so close to the bridge, they may as well call it Bridgeview Condominium. So this is the excavation that's going on, and this is the Bay Bridge anchorage. And this is Harrison Street, where this photo is taken from. So we were able to look at the construction drawing, and this Bay Bridge anchorage was founded in bedrock. It's called sandstone. You can see that if you blow this up, it'll be, this date's probably 1933 or 1934. That's during construction of the Bay Bridge. So we drilled a bunch of borings, and this is the Bay Bridge anchorage. This is our site, okay? And this is like 20 feet away. We take a cross-section through here. This is what it, the subsurface condition consists of fill. That is fill that fill that was placed after the excavation of the Bay Bridge anchorage. And here we have bedrock. We call it shell and sandstone. You notice here the elevation is minus 21.67 feet. This is the shoring plans. By the Bay Bridge anchorage, the excavation will be 30 to 40 feet, and we're planning to use soldier pile and lagging with rakers. The soldier pile is a wide flange W14 placed in 2 feet diameter holes at 7.5 feet on centers. And the rakers, there are 2 rakers, or 2 rows of rakers rather. One is 18 inch in diameter, and the other one is 12 inches in diameter. So this is the step of the construction. This is 20 feet away, and this excavation will go down to minus 27.5 feet. So the excavation will be about 6 feet below this bottom, 6 feet. And this is about 20 feet. So if you take the inclination of this, that will be like 6 divided by 20 is what? 30%, 0.3. And the excavation will be in this manner. First, you want to install this soldier pile, and then you excavate to this level, and then you install the lagging, this wood lagging. And then you excavate to this level dash line. You install these whalers and these rakers, that big pipe, 18-inch pipe. And then you excavate to this level. And then you install whalers and rakers. And then lastly, you excavate to this level. And that's it. So from soil mechanics point of view, you know, you have this. This is above, you know, 2-to-1 line. So intuitively we can say that this excavation should be safe. However, looking from the point of view of the Caltrans is California Department of Transportation, that has the authority to approve or disapprove your plans. It's not as simple as that, because the person in charge say this to me, that Bay Bridge is very important infrastructure or roadway. And if something is wrong with the anchorage, something large movement, something like that, the Bay Bridge has to be closed for safety of the travelers, and he doesn't want to be the person who stopped to close the Bay Bridge, which I understand his point of view. So how do we prove that this excavation will be stable? I find no simple solution or closed form solutions available. So we look at the finite element method. We use this is in the old days, about 1998, I think, this project. So about 20 years ago. We seldom use Plexus, but Plexus already in existence. So we use Plexus to, so this we gather that this you can have about 0.1 inch of movement here, but for the structure, based on this number, you have very little movement. So that movement is tabulated in the next. You see, what we have, we saw that the movement is less than 1/100th, 0.01 inch of movement. So it's less than 1 millimeter. And under seismic condition, using seismic coefficient of 0.2, we still have less than 0.1 inch. 0.1 inch or what's 0.1 inch? About 2 millimeters of movement. So with that, Caltrans approved our plans, and we constructed. So this is the construction of the soil nailing system that is used for 3 sites, not for the site that we use soldier panel lagging. What is soil nailing system? Soil nailing system is, this is the schematic diagram soil nailing system. Soil nailing system is basically rebars or tendons that you place in pre-drill holes. These pre-drill holes are spaced at about 5 to 6 feet on centers, and then grouted. And then over here, you have this shotcrete facing that is reinforced with wire mesh. If you have permanent soil nailing wall, you have another layer here. And for that, you have to have a studs, shear studs. But in this case, if you have a just temporary shoring, you don't have to have a shear stud. So you just put a plate and a nut to install this wall. And you do that in stages. First, you make a cut about 3 to 5 feet, install your first row of nails, and then you shotcrete the face, you go another level, you do the same thing, you repeat it until you go to the bottom of the wall. And this soil nailing system, it was invented in around 1970s. And the first project with this soil nailing wall system used in Indonesia was in the early 1990s. I think it's at the project called Gedung GKBI. Gedung GKBI is located at the Bendungan Hilir, dekat Jembatan Semanggi. So that is the system that was used first in Indonesia on a major project. So this is the view of the soil nailing wall. This is the mat. This is the site that is adjacent to the Bay Bridge anchorage. This is step 2 or 3. This is the whalers that we saw before, and this is one of the steps where the rakers have been installed. This is the first row anchors, and this is a situation where the wall is completed. This is the second row anchors. The second row rakers rather than not anchors. Rakers. Rakers is inclined support, internal bracing, inclined internal bracing. So this project has been completed successfully, no movement detected, so everybody was happy. The second project that we're gonna discuss is the Century, which is a deep soil cement mixed wall. Maximum depth of excavation is 54 feet. It's located in this area here. This is the project site plan view. This is 2nd Street between Mina and Thomas Street. This is the future, at that time, was the future high-speed rail below ground. I've been working on this project for maybe like 20 years or so. Until now, it's not completed yet. That's what happens. Sometimes you work 10, 20 years, never happen. So this building is going to be like 45-story tall. It has a 2-story basement. However, the original plan was to have 3-story basement on a mat foundation. So this is the bottom of the basement. It's about 54 feet. The bottom of the excavation, it was gonna be supported on the mat foundation. The soil conditioning consists of fill, dune sand. Marsh deposit is basically as medium to stiff clay, and then you have a dense sand here. Groundwater table is pretty high. So because of the high groundwater level, we were using what we call deep soil cement mixing system here, DSM, or soil cement mix wall. So it's constructed using multi-axis drill system, and at the alternate locations, steel beams were placed into the ground. So let me go back here. Initially, this was going to be the first top-down construction that is going to be done in San Francisco. I don't know how many top-down construction have been done in Jakarta. I think there has been 1 or 2. I'm not too sure. So basically, we do not use tiebacks. We do not use internal bracing, but rather we use the building slabs as the internal bracing. So what we do is we install the shoring walls first, and then we install king piles or king posts to support the slabs during construction. And then we install the street level slab, and then we excavate with a small excavator below to come to the basement slab number 1. So we cast the basement slab number 1, and then we go down another level. We cast the basement level slab number 2, and so on until we come to this level. We cast the basement wall, the mat foundation. So that is top-down construction, which has not been, to date, has not been used in San Francisco. So So this is the construction of the soil cement mix wall. This is the site. You have an adjacent building here, not very tall, maybe like 3-story. But across the street, you have tall building, like 20-story. And over here, you have a brick building here. So because of that, we cannot use tiebacks because you have adjacent buildings not too far from your site, and they will not like you to install tiebacks beneath their properties because these tiebacks may present a hindrance, an obstruction to their future development of the site. So go back to the instruction. This is multi-level. You can see this is a triple axis drill pier, drilling equipment. It was done by, at that time, was a Japanese company called Seiko, exactly the name as your watch, Seiko, S-E-I-K-O. So looking at the closer view, this is the triple axis. So basically, they advance this these augers down to the ground, and at the same time, they injecting and mixing the soil in situ. In situ means in place, with cement bentonite slurry. So because of that, the soil and the cement will form a stronger soil. And the specification requires that the 28-day strength, of these specimens recovered from the mixture is 200 psi, pounds per square inch. And also because this wall is impervious, we also recover samples and then test it for its permeability. The permeability should be less than 10 to the power of -6 centimeter per second. So that's more like the permeability of clay. So we did that, and they were the cylindrical strength and the permeability of the samples that we recovered from the ground were fine. They are within what we specified. So that is good. During construction, we also want to monitor the movement. So we install, instead of installing inclinometers in pre-drill holes, we attach the inclinometer to the beams, and we just lower it into the ground. So when you do that, this is the process of lowering the steel beams into the ground. So because if you lower these steel beams soon after the drill holes are completed, then it will be easy. This will just drop by itself by its gravity. So in the final condition, this is the final condition. As I showed earlier, this is the steel beams that is spaced at about 4 feet apart. So the shoring walls were completed. However, the TJPA, the Trans Joint Power Authority, that has authority over the high-speed rail system, they realign the track, realign the alignment of the railway such that it's intrude to our site. So because of that, apparently we cannot coexist. So they acquire this land from the developer. So the developer cannot develop this any further. This is the Four Seasons Hotel. This is the concrete diaphragm wall. And And this is the only concrete diaphragm wall that has been constructed in San Francisco. I think it's very common in Asia, more expensive than the salt cement mix wall that I described earlier. So it's seldom used. However, this wall can be used as a permanent wall. So the advantage is that you do not have to build your permanent wall. You can just use this, number one. Number two, you save some space because you don't need to build a second wall. So you have more space in your basement. The critical feature of this project is adjacent to BART, an existing building. So this is the view of the project. This is of course a model. This is the Four Seasons Hotel in the model. So this is if you walk from this side, you can see, take a picture that this is what happened. This is the Gary Street, I believe. So this is the Four Seasons Hotel and Tower. This is a 36-story building. Over, I believe it's 4 or 5 level of basement. So it's adjacent to this 6-story brick building. It's adjacent to Marriott Hotel and adjacent to a 2-story brick building behind this. So there's a lot of buildings. And also it's adjacent to BART and Muni lines underneath Market Street. So it's very crowded. So this is the site. So this is Market Street, and this is Marriott Hotel. And this is the footprint of the tower. However, the footprint of basement is go all the way to the property line. Okay. Here you have this, what we call 735 Market Street, which is a 6-story brick building. And here there's an abandoned electrical substation building, 2-story. So because of this situation, we can use tiebacks in most of this, below the basement, of course. But over here, you can, BART, very rapid transit, will not allow you to use tiebacks because they have tunnels. So here we have to use internal bracing, which is diagonally oriented, like this, okay? So like this. So part of the retaining system is tiebacks, and part of the retaining system is internal bracing. It's a mixed bag. So this is a soil condition. We have fill, dune sand, marsh deposit, clay sand, silty sand, old bay clay, silty sand, and this is probably alluvial deposit. So the excavation is 70 feet, so it's right on top of right here. So the building is, as I said, it's a 36-story building. So it weighs about what, maybe 7,000 pounds per square foot, roughly. And the soil excavated is about also the same, about 7,000 to 8,000 square feet. So this is like a compensated foundation. So you don't need any piles, but you need a mat because you will have some differential salmon within your foundation. So you need a mat. So as I mentioned, we're going to use concrete diaphragm wall. So before you install your concrete diaphragm wall, you have to install these guide walls, right? Guide walls, and you use this clamshell to dig your soil. And then you put your rebars. This is end plates. And then you cast the concrete. Of course, the excavation is maintained stable by using bentonite, mixture of bentonite and water. So this is a pouring concrete. And this is the this is looking south. This is looking south. This is the 2-story electrical substation that has been abandoned. This is the 7-story, 6 to 7-story brick building to the east side of this project site. This is looking south, as I say. So you see that we use tiebacks wherever we can, but on the side of Market Street, you cannot use tiebacks. You have to use this diagonals, internal bracing. This is one side of the facing along Market Street. Market Street is running in this direction. So the internal bracing, you have this diagonals, cross-lot bracing kind of thing. But here we have another layer, another row of rakers, as I can see here, show later. So this is Market Street, where bar tubes are underneath it. This is the 7-story building, and this is Marriott Hotel next to it. So we have this. This is the diagonals for the first row of internal bracing. This is diagonals, second row of internal bracing. And this is your rakers that is kicking into your mat. So the mat foundation was partially cast first, and then you use the mat to kick into this the ground. So let me show you a little. So this is a situation for your the third row or raker of the foundation. So we have inclinometer here, and also we have another one here, so we're going to look at number 2 and number 4. In number 2, you can see that this movement here, this is the mat. So the movement here is about maximum. The lateral deflection is about maximum. It's about 0.8 inches. It's about 2 centimeters. However, there's something fishy going on here. I think what happened is that this wall is not extended to the ground surface because of the vault underneath it. So the wall stops here. So this is nothing to do with the movement of ground, but rather because of the void space kind of a thing. So this movement is only 0.8 inches, and that happens to be about 0.1% of the excavation height. So that's pretty good. So everybody was happy with this 0.8%. If you look at the increment number 4, which is farther away, it's about 15-20 feet away from number 2, the movement is even smaller. It's about 0.4 inches, about 1 centimeter. Now we come to the last project, number 4. We are about 6:10 now. I think I may go to about 6:20, but I think if there are a lot of questions, we can extend this up to 2 hours today. If anybody is interested to ask questions after the talk at 6:20, we can have another half an hour of question and answers. So this is project number 4 is Ocean White Center. This is the building was going to be Ocean White Center. So fortunately for me, my colleagues have prepared these slides for the internal presentation within the company. So my colleagues, Justin Ray, Scott Walker, and Laurie Simpson has allowed me to use their slides for this presentation. This is Ocean White Center, what was going to be the second, one of the tallest building in San Francisco. Let me show you the plan. So there are two towers. This is the green tower, and this is the purple tower, right? So the green tower is gonna be 910 feet tall, and the purple tower is gonna be 630 feet tall. There are gonna be 3 to 4 basement levels. Excavation will be 65 to 72 feet deep, and the foundation consists of large diameter drill shafts or bored piles extending to bedrock. Now, the critical nature of this project is this. We have across the Stevenson Street, we have this 535 Market Street building that is 40-story, and they are supported on shallow piles. So they are not very deep piles. We also have 18-story building here, what we call 25 JC Street, 240 feet tall, also on shallow piles, or short piles. Maybe a better word is short piles, not shallow piles. We have 2 adjacent buildings here, 1 acre, and this one here, that is 6-story brick buildings on shallow foundation. So we have 6-story building on shallow foundation, 18-story building on short piles, and 40-story building on short piles. So that's very challenging, very challenging. So if you look at this cross section through here, okay, this is what it looks like. So you have this 18-story building. Don't pay attention to this. This is, I think it's a typo. It's only 18-story building, JC Street. So the piles are terminated above the future bottom of the excavation. So we have to design the shoring wall for the surcharge pressure coming from this building load. But that's very typical what we have to do. This is the soil condition. You have this fill, dune sand, marine deposit, colma, or bay clay, sand deposit, alluvium, and bedrock. So this is the line of the excavation. Okay, this is the shorter building, 630 feet, 32 tower 2 building. This is the taller building, 910 feet, and this is the piles. Before we do the excavation, we install 101 drill shafts or bored piles. Diameter is 6.5 feet or 2 meters. They are socketed 5 to 50 feet into the bedrock, right? So this is the bedrock. So the excavation will be 4 basement level, and will be 3 basement level. So this is the internal bracing that we have to use because there's so many adjacent buildings, and also you need very rigid internal bracing to reduce deformation, excavation, or deflections. So this is the plan view of the shoring system. So these are the diagonals. These are the cross slot bracing. These are pipes, made of pipes. And this is maybe like 36 inches in diameter. What's 36 inches is what? Maybe 90 centimeters. And this is 42 inches, I think. So this is about 105 centimeter, 1 meter 5 centi. So you can see this here, you have collars, right? Collars. The purpose of the collars is that to allow you to preload, to jack this pipe, because you don't want the deformation. So you want to preload this wall. So that's the purpose of that collars. So this is the issue what we have. We have 2 issues. One is that you have these sand lances that may blow up this excavation. So it's called basal heave for sand. Another problem is that we have basal heave for clay. Here, you may have this situation where you may, this building, 525 Market Street, which is 40-story building on short piles, they will induce pressure on this column of soil such that the soil may rotate and come up here in terms of base instability. So you call it basal heave phenomena. And this 525 Market Tower, of course, they have the geotechnical consultant. And so we have to please them to make sure that our shoring will not cause any harm to their building. So we have to do a calculation and stuff. However, looking at the this is picture showing the blowout of piping because of this pressure here. So that's to reduce the tendency for this clay layer to blow out, we have to use this depressurization pump. So we have to drill wells, pumping wells, and we have to dewater pressure here so that it will not cause any blowout. But what about this basal heave problem? So to do that, based on this a chart by Tusagi, Peck, and Mesri, for the situation that we have a factor of safety against blowout of about 1.05. So we look at this, according to Tusagi, we may have 0.35% of deflection or deformation of the ground. So 0.35% is 3 inches. So our neighbor will not allow this to proceed unless this movement is reduced. So this is deemed as unacceptable by the project team. So what do we do? Well, in this case, we do something that we have never done in San Francisco, is to use buttress walls. So this is the excavation part that is close to the 525 Market Street. We use these buttress walls. This buttress wall is made using salt mix wall methods. So basically, we create a wall that is hard, has a compressive strength of about 200 psi to buttress this wall. So let me install. Let me connect my computer to the battery source.
Ya, baik Pak Hadi, mungkin kita bisa selesaikan sekitar 5 menit lagi. Jadi karena sudah hampir jam 6.30 PST, acara akan kita ubah sedikit. Jadi setelah presentasi, kita foto bersama untuk closing secara formal. Setelah itu kita akan buka sesi Q&A selama 30 menit. Kita yang mau stay silahkan untuk langsung berkomunikasi dengan Pak Hadi.
Oke.
Kita akan lanjut, Pak.
Saya akan percepat. Jadi ini kita pakai ini, lalu kita harus analisa ini, kita pakai analisa pakai Midas program. Setelah kita pakai Midas program yang 2-dimensional, ternyata deformasinya masih 3 inci. Jadi kita pakai Midas program yang 3-dimensional Midas model seperti ini. Ternyata kita bisa mengurangi deformasi sampai 1,5 inci, dan itu diterima oleh project team. Jadi kita setelah itu kita mulai melaksanakan kita punya wall, soil cement wall pakai sistemnya ini, trader bukan pakai drill equipment. Ini ada pipa-pipanya yang tadi saya perlihatkan itu di denahnya. Ini ada 1 inkilometer, saya mau kasih lihat inkilometer, pembacaan kilometer. Ini adalah pembacaan kilometer. Ini mula-mulanya tentunya ini adalah reference point. Kemudian setelah penggalian sedikit, 1 level kita baca, level kedua kita baca dan seterusnya. Jadi pada tanggal 7 Juli 2010 kita sampai di yang gambar biru ini, hijau ini, hijau. Nah setelah itu, setelah kita gali dan pasang pipa-pipanya, terus kita cor itunya, matnya. Ini kan mat, pile supported mat. Setelah itu kan kita bangun ke atas. Bangun ke atas itu kan kita harus copot itu kita punya bracing. Setelah bracing kita copot, ternyata masih ada deformasi, masih dia naik lagi. Jadi karena apa? Karena pipa itu kekakuannya lebih tinggi daripada kekakuan basement slabs, sehingga akhirnya sampai atas ternyata deformasinya adalah seperti ini. Jadi ternyata kita bisa mempertahankan deformasinya itu di bawah 0,8 inci atau 2 cm. Jadi itu adalah kira-kira 0,1% daripada excavation. Itu adalah satu keadaan yang sangat baik, excellent. Jadi proyek ini berhasil. Dibandingkan dengan theoretical model 3D Midas memprediksi seperti ini, 1,6 inci. Jadi kita pelaksananya ternyata dari pelaksanaan kita bisa mengurangi defleksi dari 1,5 inci sampai 0,8 inci. Kemudian mungkin ada yang tanya, bagaimana bangunannya udah selesai? Well, kalau basement udah selesai, tapi ini kan ocean wide, apakah kalian tahu ocean wide itu adalah dibangun oleh Evergrande dari China. Evergrande sekarang lagi mengalami masalah keuangan di mana-mana, sehingga proyek ini sekarang tidak dilanjutkan dan akan mencari pembeli. Jadi itu sekian saya punya presentasi.
Ya, baik. Terima kasih Pak Hadi atas presentasinya. Ini menarik sekali dan banyak sekali pertanyaan. Tapi supaya kita tetap stay dengan jadwal, jadi acaranya saya modifikasi sedikit. Sekarang secara formal kita akan foto bersama dan closing. Setelah itu seperti yang tadi Pak Hadi bilang, beliau bersedia untuk stay sampai setengah jam lagi untuk Q&A, begitu. Jadi pesan terakhir dari ICESNA ini ada email ICESNA. Jadi kalau memang ada rekan-rekan sekalian yang berminat untuk menerima notifikasi webinar ICESNA selanjutnya, silahkan kirim informasi rekan-rekan sekalian ke ICESNA. Atau bahkan kalau misalnya mau propose apa topik yang menarik untuk webinar selanjutnya, silahkan juga email ke email ICESNA. Demikian saya pikir saya secara formal tutup, walaupun kita akan lanjut lagi dengan sesi Q&A yang lebih non formal. Terima kasih atas kehadiran rekan-rekan semua. Terima kasih juga kepada Pak Hadi yang sudah membagikan ilmunya yang pengalaman yang banyak sekali pada kita semua. Dan kita akan foto bersama. Edwin, gimana ininya?
Siap. Sekarang boleh turn on video ya semua. Mohon kesediaannya. Oke. Ada banyak nih ya.
Saya stop share dulu ya.
Iya. Nggak apa-apa. Oke, 3, 2, 1. Oke, lembar pertama. Oke. Kita ke lembar kedua sekarang ya. 3, 2, 1. Ke lembar berikutnya lagi ya. Bentar. 3, 2, 1. Dan ini kayaknya 3, 2, 1. Dan selesai. Terima kasih Bapak Ibu, saudara-saudari sekalian.
Terima kasih. Silakan. Ini tadi.
Edwin, ada berapa yang masih ada berapa orang?
Ini masih banyak Pak, masih 90, hampir masih semuanya hampir masih stay.
Semuanya masih stay.
Ya, kemudian tadi ada beberapa pertanyaan, lumayan banyak yang saya sempat capture cuma beberapa. Mungkin saya bisa share. Ya, ini beberapa yang sempat saya capture, tapi ada lagi terusannya, cuman kita bisa bahas satu-satu. Yang ini cukup yang lumayan teoretikal, mungkin kita bisa mulai dari sini Pak Hadi. How to check if passive capacity will be insufficient.
Mana yang box mana ini?
Yang ini Pak, bisa ngelihat kursor saya?
Tunggu, saya pindahin ininya. How to check if passive capacity will be insufficient. Itu harus dilakukan ini desainernya harus ini begini. Jadi kita di San Francisco kita akan memberi Geotechnical Consultant akan memberikan design pressure dari dinding ini dan passive pressure, biasanya allowable passive pressure. Dan itu harus dicek oleh desainer setelah dia memasukkan resistance daripada tiebacks atau resistance daripada internal bracing, apakah lateral stability-nya bisa tercapai. Kalau tidak bisa tercapai dengan data-data yang kita rekomendasi, itu bisa embedment-nya bisa diperdalam sehingga passive pressure-nya bukan passive pressure, passive resistance bisa menambah yang kekurangan itu. Jadi itu passive capacity akan diberikan oleh Geotechnical Consultant di dalam laporannya.
Oke. Baik, ya yang barusan pertanyaan dari Pak Junanta Chandra. Pertanyaan selanjutnya ini ada beberapa yang berhubungan dengan project Bridgeview Condominium. Yang pertama, any details can be shown of the rake strut well joint. Dan kemudian selanjutnya in the first example of Bridgeview Condominium, does the raker transfer the load from the wall to the rock layer? So mungkin Pak Hadi silahkan kalau mau jawab yang dua ini sekalian yang berkaitan dengan Bridgeview Condominium. Kalau perlu show gambar bisa share juga kembali presentasi Pak Hadi.
Tapi masalahnya karena tidak ada detail gambar. Mengenai pertanyaan pertama, any details can be shown on the raker strut joint, weller joint itu adalah struktur. Jadi itu ada wellernya itu kan ada besi berbentuk seperti H atau I gitu kan. Nanti kemudian dari rakernya kan ada, itu harus dipotong 45 derajat misalnya dan dikasih plat. Dan plat itu akan digabungkan dengan weller dengan dilas misalnya. Itu adalah salah satu yang umum dipakai. Kemudian pertanyaan kedua, example of bridge raker transfer the load rock layer ya. Jadinya itu rakernya itu akan disupport oleh shallow foundation, footing, di mana footing itu mendapatkan daya dukungnya dari rock yang di sana. Jadi itu harus ditransfer. Dan ini untuk mengurangi pergerakan juga biasanya harus di preload biasanya.
Oke, saya pikir ya lumayan cukup jelas. Kemudian ini ada pertanyaan berkaitan dengan proyek yang ketiga, Four Seasons Hotel. Was top-down construction considered as one of the options before? Any particular disadvantages of using top-down for this site? Ya, saya pikir top-down construction juga sekarang lumayan banyak di Jakarta dan misalnya di Singapura. Nah, kalau pengalaman Pak Hadi sendiri bagaimana?
Top-down construction itu memerlukan kontraktor yang experience. Kalau di San Francisco Bay Area,